Hello everybody. This is our discussion about Chapter 4 on descriptive methods in regression and correlation. And we'll try to explain what that means here in a bit. But if you'll recall, back in Chapter 1, we talked about the way that we gathered data and made sure that we had a representative sample from our population in order to come to a fair set of conclusions or inferences about that data. In Chapter 2, we talked about graphs, and those graphs included things such as bar graphs, pie graphs, histograms, and stem and leaf plots, and so on. In that organization and the way we organized the data, we were only looking at one variable at a time. Now, in Chapter 3, we talked about things such as being able to find a mean, a median, and a mode, or being able to find the standard deviation and how far all of that data is spread out. But in each of these cases in Chapters 2 and 3, we concentrated on dealing with one variable at a time. What if we have two? Well, then we need a different way of graphing this kind of stuff. And this is not just some sort of teacher torture device that we invent. What we're looking for is a way to relate two variables to one another. For example, we might think that there's a relationship between the variables of the rate of smoking and the rate of cancer in subjects, right? Or we might think that there's a connection between weight gain and weight loss and overall health costs, for example. Different things like that. If we can find a relationship between these variables, then it might give us some more information and insight into the way that these variables deal with the actual relation. So this is a great application. So the very first part of this section, I'm going to talk about linear equations in one variable. And this is really sort of a reminder of some of things that you've probably seen in an algebra course or here at New England Tech in a MA125 Tech Math 1 course. So a lot of this is a reminder from some old material, but we'll need it in order to help us figure out what's going on with the rest. So let me start with a discussion about linear equations with one independent variable. Let's start with the equation of a line. Now, the way it's put here is that we're told a linear equation, the equation of a line is given as y equals b sub 0. That's a subscript 0. So b sub 0 plus b sub 1 times x, where the number b sub 0 is called the y-intercept, and the number b sub 1 is called the slope. Well, if you recall from MA125, we would have written this as y equals mx plus b, where m is the slope and 0b is the location of the y-intercept. We're just changing the notation here slightly. When we talk about a slope, remember the slope is sometimes referred to as rise over run, right? So we call this rise over run of the line, and it tells us something about the steepness of the line. Rise over run is meant to indicate that for every change in y, our rise, there's some change in x, and that's our run. So y2 minus y1, right? If we have point number 1 on our graph and point number 2 on our graph, we get the change in the y values and divide that by the change in the x value, and we call that our slope. The point 0b is the y-intercept, and that is the point where if we get the equation of this line and we let x equal 0 in that equation, we're going to find that y is equal to b sub 0 in this formulation right here. So this is just sort of a reminder of that equation. And let's go through an example, the first one on your handout that describes this. Let's find the slope and the y-intercept of the line with the equation y equals 7 minus 2x. Well, if we apply the formula here, the formula states that we have y is equal to b sub 0 plus b sub 1 times x. And b sub 0 is the y-intercept, and b sub 1 is the slope. So in our equation, we have y equals 7 minus 2x. So if we equate these one for one, that means b sub 0 is equal to 7. And b sub 1 is equal to negative 2. Remember, the signs count right here. If we say 7 minus 2x algebraically, that's really 7 plus negative 2 times x, even though we don't really state it that way typically, right? It's the same thing. So that means that our slope is negative 2. Practically, what does that mean? Our y-intercept will be at the point, the coordinate point 0, 7 on our graph, and the slope will equal negative 2, which means that the slope is going to be negative 2. If we treat it as a fraction, negative 2 over 1. We could treat this as a rise over run situation. We use the term rise kind of loosely here because if we have a rise of negative 2, that means we're actually going down, right? Here, let me graph this line for you so that we see it. If we say it's passing through the y-intercept at 0, 7 on an xy axis system, that means we would find the point 0, 7. There it is, right? It's when x is equal to 0, y is equal to 7. That's a coordinate point. And the slope says every time you go to the right one, run 1, go down 2. So if I were to go to the right 1 point, I would have to go down 2 points to 5, right? So the point, for example, 1, 5 would be on the graph. How do I know? Well, we can also always substitute this in. If y equals 7 minus 2x, then y equals 7 minus 2 times 1. That is, y is equal to 5, and that is the coordinate point 1, 5. And we could keep going this way, right? Every time we go down 2, we go down 2, we go to the right 1. So, for example, we would have 2, 3 on this graph, and so on down the line. So now we could graph a line that passes through these points here. I'm going to do my best to kind of get it in there just about right. Make it parallel to the points and just move it to the right place, I hope. Let's see. There we go. That would be about what it would look like right here. 7 minus 2x, more or less. This is the slope-intercept form of the equation. We called this in the previous course, so we'll use it here. Okay, so not too bad. Now let's apply this a little bit right here, right? There's a couple of things that we need to know about the slope. The slope, B1, that we're using, means that if we have a positive slope, let me get my pen going here again, gosh, a positive slope B1, right? That's why they say B1 is greater than 0. That's sort of the abbreviation for a positive slope B1. That means that the line's going up as we go to the right, right? So it's an increasing slope. If we have a negative slope, that means that the slope is going down, right? And that's what we saw in our last example. The slope was negative 2 in that case. So if we've got a negative B1, that means this line is going to be decreasing as we go from left to right. Now, it's always possible that the slope is 0. If the slope is 0, that means that we have a horizontal line. And that's important for us to know. So we know the differences between each of these here. Let's try this out. What could we say about line A? Well, that's a good question. Let's see. We have y equals 5.3 minus 0.75x. So we want to know about the slope. In this case, our slope is B1. We use the letter B1 designation for that. Is equal to negative 0.75, right? How do I know it's negative? Well, remember that our model goes y is equal to B0 plus B1x. So every single time we see this, we have to say, well, how is this like that? Well, in the first case, y is equal to 5.3 plus negative 0.75 times x. Right, that's our slope. B1 right here, Yeah, in this case, B1 is equal to 1.53. So this slope right here, B1, is decreasing. This slope B1 right here is increasing. What could we say about the next one? Well, in this case, where's B0? We don't see it, right? If we don't see it, you can always think, well, if there's no B1 term, then we treat it as a 0. So y in this case is 2.71 plus 0x, right? There's no x right here, so since it's 0 x's, we say that, well, that means that B1 is equal to 0, and therefore this last one must have a horizontal slope. All right, not bad, right? These equations of lines, very useful for us in a lot of ways. We use them to do different types of tasks. Let's try one from physics right here. If a ball is thrown straight up in the air with an initial velocity of 64 feet per second, then according to the laws of physics, if you let y denote the velocity of the ball after x seconds, y will be equal to 64 minus 32x. So it wants to determine what B0 and B1 is for this linear equation. Well, right, if we were doing our matching one for one like we had been doing before, what could we say right here? Well, in this equation, it is certainly the case that B0, which is our y-intercept, is going to be 64. And so this graph would pass through the point 0, 64, right there. That's what it looks like. 0, 64. And it would have B1, which is our slope, equal to negative 32. So every time we go down by 1 second, we have to go down by 32 seconds, right? So if we were going to determine the velocity of the ball, let's say after 1 second, well, after 1 second, my scale's a little bit off down there because I'm going to have to get a few points out there. So we'll consider each one of those points down there 1 second. After 1 second, I'm already at 32 feet per second. How do I know? Well, substitute it into the equation, right? At 1 second, y is equal to 64 minus 32 times 1, right? Which is to say at 32 feet per second. So that's a 32 down there. Kind of hard to read, but there it is, okay? What happens at 2 seconds? Well, y equals 64 minus 32 times 2, which is to say y is equal to 0, right? So at 2 seconds, we have a velocity of 0. Let's do 3 seconds, right? At 3 seconds, it would be 64 minus 32 times 3. 32 times 3 is 96, and 64 minus 96 is a negative number. It's equal to negative 32, right? So we would go down to negative 32 at 3 seconds here. Right? Finally, at the 4 second mark, at y equals 64 minus 32 times 4, which is like saying y equals 64 minus 128, you get negative 64 seconds, right? So let's graph our function here. I'm only using 3 points on my function, but we could go on if we wanted to and find all of them. We're going to graph our line. So let's go ahead and get a line that passes through these points and show it off here. I'm going to show it in red. See if this works here. Let's see if I can get it about right. Oh, no. Let's see if I can graph my line a little bit closely to these points right here. I aimed a little poorly, but not too bad. That's about what it looks like. All right, so this is my line right here. If I were to plot my correct points, they would be on this line, right? So if I were to go through and I were to plot the point 132, yeah, I aimed a little bit badly. The point 20, the point 3, negative 32, there it is, right? 3, negative 32, and so on, right? Okay. Use the graph to visually estimate the velocity of the ball at 1.5 seconds. Then calculate the velocity exactly using the linear equation. Well, if we were to estimate it visually, I'll go to a green marker right here and say, well, here's about 1.5 right here, right? If this is 1 and this is 2, 1.5 is right in the center. So what we do is we go to the line and we find where that would meet, and then we look over to the side to figure out what the value would have to be. And I'm estimating, based on my line for part D, that it looks like it should be maybe 24. We'll put that with a question mark right there, right? Because that's what we're looking to see. Does it look like it should be about 24? My line might not do it justice in the way that I've drawn it right here, but let's try it out. If we were to put this in, y would have to equal 64 minus 32 times 1.5. Let's see, what is 64 minus, let's see, 32 times 1.5 is going to be 32, and then half of 32 again, which is, let's see, half of 32 is 16, right? 32 and 16 is 48, right? And then you subtract those two and you get, well, sure enough, right? We get 24. So it looks like it should be exactly 24 then. And we did good, right? There it is. So that is our lecture on lines.